Hello, so today we're going to have a look at shapes of molecules and polyatomic ions. These are determined, the shapes are determined by, it depends on the atoms that are present in them and the arrangement of electron pairs. Okay, now there's some molecules that have pairs of electrons that are not involved in bonding, and we call these non-bonding pairs lone pairs, so you'll see this in some textbooks. So a non-bonding pair of electron is known as a lone pair of electrons. For example, water. So if we have a look, this is a model of a molecule of water. So we've got the oxygen atom in the center, the two hydrogens. Okay, these represent the bonds. And then these two kind of lobes here represent non-bonding pairs of electrons or lone pairs of electrons. So we've got H2O, and then we've got a non-bonding pair of electron and a second non-bonding pair of electron on the water molecule. Okay, so it's a 3D structure. So we're going to use valence shell electron pair repulsion theory, which is shortened to VSEPR theory. And what this looks at is the total number of bonding and non-bonding pairs of electrons. And that's what you have to consider when you're looking at the shapes of molecules and ions. You probably remember from National 5 that we just kind of taught you if it's got 5 atoms, then it'll be tetrahedral. If it's got 4 atoms, then it would be trigonal pyramidal, but we have to look a bit more in depth for advanced higher. And these can be used to predict the shapes of molecules and polyatomic ions. So the way that you work out the total number of bonding and non-bonding pair of electrons is you look at the central atom. Now the central atom will be the one that there's only one of in the molecule. So in the example of water, there's one oxygen, so oxygen is the central atom. You take the total number of valence electrons, so the total number of outer electrons on the central atom, and then you add one for each atom that is attached. Okay, so for example, let's have a look at water. So water, for example, the central atom is oxygen. It has 6 outer electrons, and then it has 2 hydrogen atoms attached. So 6 plus 2 gives us a total of 8 electrons. It doesn't have a negative charge, it doesn't have a positive charge, and then we divide the total number of electrons by 2, and that gives us a number of electron pairs. So if we divide the total number by 2, then we get 4 electron pairs. And you might be thinking, well, hang on, there's only 2 bonds in oxygen. But remember that when we're talking about the shapes at advanced higher level, we have to consider the non-bonding pairs of electrons and the bonding pairs. In the molecule of water, there was 2 non-bonding pairs and 2 bonding pairs. So you can use these equations below to help you. Unfortunately, these ones are not in the data booklet, so the ones you're just going to have to learn. So to find the number of electron pairs in a neutral molecule, it's the number of outer electrons on the central atom plus the number of bonded atoms, so the number of atoms that are joined to that central atom, and then divide that by 2. If you have a negative ion, you do exactly the same, the number of outer electrons on the central atom, the number of bonded atoms, but then you add the charge, you add the extra electrons that come from that negative charge, and then divide the overall total by 2. If you have a positive ion, then it's your number of outer electrons on the central atom, add your number of atoms that are bonded to it, and then you subtract the charge. Divide that by 2 to give you the number of electron pairs. You should always get an even number of electrons, which will then give you a whole number of electron pairs. If we have a look at ammonia, okay, the central atom is nitrogen. Nitrogen, excuse me, is in group 5, so it has 5 outer electrons. There are 3 hydrogens bonded to it, so we have 5 plus 3 equals 8. Divide that by 2, and that gives us a total number of electron pairs as 4. 3 bonded and 1 non-bonding pair. So here is a molecule of ammonia. Here is our central nitrogen atom with the 3 hydrogens attached. You can see that it forms, and the one non-bonding pair. Actually, it's got a tetrahedral structure, but when we have the non-bonding pair here, we can also call this a trigonal pyramidal or pyramidal structure. Okay, so there are 4 electron pairs, 3 of them bonding and 1 of them non-bonding. The electron pairs in any molecule or ion are negatively charged, and therefore they will repel each other. And they are arranged in such a way so that the repulsion is minimized. So basically the electron pairs try to get as far away from each other as possible. So they're arranged to minimize repulsion and maximize separation, social distancing in electron pairs. The arrangement of electron pairs around a central atom is linear if you have 2 electron pairs, trigonal planar for 3, tetrahedral for 4, trigonal bipyramidal for 5, and octahedral for 6 electron pairs. We're going to have a look at some examples. These are the classic examples that you will see. Not always asked about, sometimes they throw in a few that you have to work out, but they'll all follow the similar sort of pattern. So the first one we're going to look at is beryllium chloride. So beryllium is in group 2, so it has 2 outer electrons. There are 2 chlorines joined to it, so our total number of electrons is 4, divided by 2 gives us 2 electron pairs. If you have 2 electron pairs, the furthest away those electron pairs can be is by being linear, by having a 180-degree angle in between them. So this becomes a linear molecule. So here we've got our beryllium atom, our 2 chlorines joined, and you can see that this molecule is linear. Okay, all the atoms are in a straight line. If we have 3, sorry, I should have highlighted that. We'll just highlight the fact that there's 2 electron pairs. It's linear. If we have 3 electron pairs, the shape is trigonal planar. Notice that's different from trigonal pyramidal or pyramidal that you've met before. The classic example for this one is boron trifluoride. Boron is in group 3, so it has 3 outer electrons. There are 3 fluorines joined to it. Total number of electrons is 6. Divided by 2 will give you 3 electron pairs. The furthest away that they can get, each electron pair can get from each other, is by forming a planar triangle with a bond angle of 120 degrees between each atom, each electron pair. So this is a molecule of boron trifluoride. Okay, you can see it's planar. Okay, all the atoms are in the same plane. It's a flat molecule. The bond angle between each of the electron pairs is 120 degrees. You need to know the bond angles. You need to know the names as well for advanced higher. So this is boron trifluoride. If we have 4 electron pairs, then the shape is tetrahedral. You'll be familiar with this one from National 5 chemistry, for example, methane. Okay, carbon's got 4 electrons on its, because it's a central atom, with 4 hydrogens attached, adds together to make 8, divided by 2 gives us 4 electron pairs. Okay, in this example, in fact in most tetrahedral ones, the bond angle between the electron pairs is 109.5 degrees. Okay, so here is our molecule of methane. I'm sure you've all built one of these at some point. Okay, carbon in the center, the 4 hydrogens arranged tetrahedrali around that central carbon, and the bond angle between each electron pair is 109.5. Okay, Okay, again, you need to know bond angles as well as structures. Moving further on, if we have 5 electron pairs, this is called trigonal, bipyramidal, or bipyramidal. Okay, so 5 electron pairs. So if we have a look at phosphorus 5 chloride, so phosphorus itself has 5 outer electrons. There are 5 chlorines joined, so 10 electrons in total, 5 electron pairs. This is an unusual structure because it has 2 different angles within it. So if we align it, so we've got an atom facing up the way and another chlorine atom at the bottom, okay? So those are planar, they're all in the same plane. You can see that around the center, we have a trigonal arrangement, okay? So between this trigonal one and this one, between each of them, there's a 120-degree bond angle. Excuse me. If I turn it on its side so we can see, these were the 2 that were vertical in the last one. Here around the center is our trigonal planar arrangement of atoms. The angle between the vertical atoms and this trigonal arrangement around the, excuse me, around the center is 90 degrees. So there are 2 different angles in this structure, 120 and 90 degrees. Okay, so that is a trigonal, bipyramidal, or pyramidal arrangement. That happens with 5 electron pairs. If you have 6 electron pairs, then we have an octahedral arrangement. People sometimes get confused because they think octahedral means 8, so you should have 8 electron pairs. It's not, it's actually for 6 electron pairs. It's because it forms 2 pyramids with square bases, which together make an octahedron. Okay, so the example for this one is sulfur 6 fluoride. Sulfur's got 6 outer electrons. You've got 6 fluorines joined to it, so it gives you a total of 12 electrons divided by 6 will give you 6 electron pairs. So an octahedral arrangement has, if I hold it vertically to start with, so there's 3 atoms in a line, fluorine, then sulfur, then fluorine again, and then around the middle, instead of having the 3 that we saw in the trigonal bipyramidal arrangement, we have 4. So in a square planar arrangement around the center. Now each of the bond angles between these atoms is 90 degrees. They're at right angles to each other. And in fact, if I turn it on its side, the vertical to the planar bit around the middle is also 90 degrees. So all the bond angles in an octahedral arrangement are 90 degrees. Okay, this video is shows you animations, which are probably better than me turning the models around to show you the different shapes involved in valence shell electron pair repulsion theory. Okay, so we've looked at ones, most of the examples we had there only contained bonding pairs. And the repulsion, I'm just going to correct that spelling. The repulsion between the various types of electron pair combinations varies and changes, and it can change the angles in between them. So we had the basic angles, okay, the ones that are given in your notes. So for linear, it was 180, trigonal planar was 120, tetrahedral 109.5, the trigonal bipyramidal was 120 and 90 degrees. There was the 2 angles in that one, and 90 degrees in the octahedral. However, when you get a mixture of non-bonding pairs of electrons and bonding pairs of electrons in the same molecule or ion, the angles can change. Okay, and this is because the non-bonding pairs have a greater repulsion than bonding pairs. And in fact, if you have a non-bonding pair adjacent to another non-bonding pair, you will get the greatest repulsion. If you have a non-bonding pair adjacent to a bonding pair, you will get some degree of repulsion. And if you have bonding pairs adjacent to each other, you will get the minimum type of repulsion. So you need to know the order of repulsion. I'm going to show you some examples that explain this as well. If we have a look at ammonia, I'm going to come back and highlight this. I'll show you the model first of all. Okay, so if we look at our model of ammonia, we have 4 electron pairs, 3 of them that are bonding and 1 of them that is a non-bonding pair of electrons. So this one, I mean, technically it has a tetrahedral arrangement, but with one of them, because it's a non-bonding, we change that to say that it's a trigonal pyramidal arrangement. Now what happens, because this non-bonding pair of electrons exerts a repulsive force on these 3 bonding pairs, it actually squashes or pushes the bonding pairs closer together. I cannot do it with this model, but what happens is that these bonding pairs will be pushed closer together. So instead of having the normal 109.5 degree angle that you would expect from a tetrahedral arrangement of atoms, the angle is actually reduced to about 107 degrees because of the repulsion, the repulsive force exerted by this non-bonding pair of electrons. So it pushes the bonding pairs closer together. Remember, a non-bonding pair to bonding pair repulsion is greater than the repulsion between the bonding pairs themselves. Okay, so it pushes them closer together. So the repulsion between the non-bonding pair and the bonding pairs is greater than between the different bonding pairs. So what happens is that non-bonding pair on the nitrogen pushes those 3 nitrogen to hydrogen bonds slightly close together, and so in fact we get a bond angle in ammonia of about 107 degrees, which is slightly less than what you would get in a true tetrahedral molecule like methane, for example. Bond angle would be 109.5. Okay, so that's the story with ammonia, which has 1 bonding pair. If we have a look at water, and again, I'm going to show you the model first of all. Okay, so here's water with its 2 bonding pairs and 2 non-bonding pairs. So this time we have repulsion between the bonding pairs, which is the minimum type. We have repulsion between the non-bonding pair and the bonding pairs, which we met again in ammonia. But now we have an additional form of repulsion, the repulsion between the 2 non-bonding pairs. Now this is the greatest type of repulsion. These 2 non-bonding pairs of electrons do not want to be anywhere near each other. So they will push themselves apart from each other. Again, they will get non-bonding to bonding pair repulsion. So these will push these bonding pairs closer together, even closer together than they did in the ammonia molecule. And in fact, the bond angle between the oxygen to hydrogen bonds is about 104.5 in a water molecule, because you have not only the repulsion between the non-bonding and the bonding pairs, but repulsion between 2 non-bonding pairs of electrons. So the 2 non-bonding pairs around the oxygen atom squeeze the 2 oxygen to hydrogen bonds closer together, and so the bond angle is reduced even further. Okay, so based on that, you should be able to do questions 28 to 36 in your question section. Some of those contain ions, in which case you need to remember to add the charge if it's a negative ion and subtract the charge if it's a positive ion. You also need, I think it looks for non-bonding molecules that have the greatest number of non-bonding pairs of electrons. You're looking for things like halogens, for example. Remember, a halogen atom, it forms one single bond, and there are 3 non-bonding pairs of electrons on every halogen atom. Okay, if you have any questions, as ever, just ask. Thank you.